Hi, this is Silvia Mazzoni. I developed these maps, and so I wanted to give you an overview of how to navigate the Directivity-Based Probabilistic Seismic Hazard in California interactive maps. We developed these maps to evaluate the different directivity models, their effects on the hazard in the entire state of California. So this is the page. I recommend you reading all these long words. There's some nice pictures to go with it. It's a nice description of the background that you have for the directivity, no directivity cases, and all the different models. There's also reports that are being published. So before you use this tool, make sure that you are familiar with what is the technical basis behind it. All right, but I'm going to go straight to the maps. So the button here takes you to the map. So you click enter, and this takes a little bit to load up the map in the iframe. So you have to be patient, especially because I'm loading up a loaded map. All right, so this is the interface, and you can see you can open up here and read the instructions. Again, lots of words, but I think it's easier to just demonstrate it. Okay, so I close the instructions. You've got a series of different pull-down menus here. So there is something about period. There's something about the data that is being plotted, the VS30 that you're looking at, and the return period. This button here is kind of cool because once you've selected the map and you want to hang on to it, you can then open it in a separate tab. So we'll do that afterwards. Whatever choices you make here in the pull-down menus, the program automatic uploads the proper map. Not only that, but you have to be careful because I've programmed this as well as I could, that what's in these menus depends on what's in the other menu bars. So for example, because I'm asking for something with and without directivity, but mostly with directivity, this is only going to be for cases of the period greater than 0.5 seconds, greater than or equal to half a second. So you see that there. But if I go here and I pick the no directivity, there's an update now. And now I've got a much wider range of periods, all right? So I'm going to go back to this menu right here, actually, first of all. So the first one was easy, actually. I showed you it's all the different periods where the PSH was done. And what you'll see here in the maps is the intensity measure plotted for all the sites. So for this case, if we go, we've got the 3 seconds, VS30 760, return period is for 2475, and right now I'm looking at no directivity. Then we also have the PSA with directivity, with the ratio of the amplification factor measured at or computed for VS30 equals to 760. And there are some cases where the directivity was actually computed for different VS30s, and I will show you that in this case. Then I've got two maps of the same thing, but now they're actually comparing in the same map with and without directivity. So these are twice the data, so they may take a little bit longer to load up. But it allows you to visualize the data in the same page back and forth, and I will show you that. Then we've got the directivity amplification ratios. This is the recommended one, which is weighted average of the different directivity models, but the recommended one has a lower bound of 1.0, while this one is purely the weighted average and therefore it has no lower bound. Then I've got the directivity amplification factor for the 3 directivity models. These are amplification factors for the ROT-D50, and these are amplification factors that you apply to compute to convert from the ROT-D50 to the fault normal, fault parallel components for the BS13. So this is something you need to read the report about if you want to go to these, because it's not just as simple as just going to fault normal, fault parallel. Then we also have data. We've got the site-specific BS30, the Z1, Z2.5, and the USURF3 fault. As I mentioned already, I have these computations were done for these different VS30s, as well as the estimated site-specific and, where possible, estimated site-specific and site-specific Z values for Z1.0 and 2.5. And then we've got the range of return periods. So there's a million different combinations that you can do in visualizing these data, and it can get quite interesting. I've also added some features to the maps. We've got the different layers. So you've got different background layers, because you see this is kind of a nice one because it's a plain map, but it still shows you where the states are, and so it's just good to get some visual. Again, it really determines what you see and how busy it is when you zoom in. All right, so I'm going to zoom into the Bay Area just because it has all the different features. If I look at, so this is actually a really nice default map. you can look at the terrain map, and this is cool because it shows you, oh look, you can actually really see where between the hillsides here where you've got the fault. So this shows you a little bit more about the topography in the area that might help you to understand, and a little bit more correlation with the VS30 almost, right? And then we have this one here is kind of funky, but it's kind of cool because it blacks out the water, so it really makes your colors stand out. If you want to make a point, this is like, whoa. And then we've got OpenStreetMap, and I'm using this as the default because it's a busy map, but you can really go down and zoom in and get a better understanding of where the city is, where the features are, and maybe more information. Okay, and so it really depends on, you know, this is something high contrast. This is a nice terrain because you could see, oh, okay, I'm in the middle of the hills right there, or I'm in the middle of the plains. And then this one is just a nice mix of a low contrast in the map, but you can still see all the features. So I thought these were handy. Then we've got different types of data. So I'm going to turn off the data itself. So typically you have a button here where you can turn on and off the data. These are the USURF3 faults. They're in the background of every map. And if you click on one of them, let's go over to the Hayward fault. If you hover over it and you catch it, it tells you what that fault is. It gives you the name. If you click on it, it actually gives you a bit more information about it. This is whatever I had obtained from the modelers about the different faults. Remember, there's so many sections and there's so much information about each one, but I thought this was handy, and then you can just copy and paste this as something that's relevant to you. Then we've got the natural gas pipelines for California. Obtain this data from the project via CEC. So these are the natural gas pipelines that we obtained the data from the CEC. Something important to the project sponsors, and it actually shows you some pretty neat information, as well as the storage sites. So again, this was important to the scope of this project and what it was developed for. So this is something that I've defaultly left out because it makes the data a little bit busy, but I left the faults on because I think they're relevant for your hazard. And then you can add a marker to this. So let's say that you've got a site. I put in some example. So I think I said it that you don't have to give it a name, but it's good to always give it a name. 37.66, comma, negative 119.223. If you click OK, it's going to place a marker, and you hover over it, says my site. All right, so why am I putting this in? Well, this site now you can say, well, how far is my site from the USURF? If you saw I zoom in, you can zoom in with the mousey wheel, which is easier, or you can use these up and down arrows, okay? Also, you can close this window here. This is just to show you where you are in the big map. So I put in this, little tool for measurements. And so you can put multiple measurements, so you pick a point. This is our site. So let's see how far we are from this tiny little fault. So I try to draw a tangent line, and then I can keep going and do other measurements, but I'm going to finish right there. And it says, okay, I'm about 20 kilometers from this fault. Who is this fault? This fault here is the Hartley Springs 2011 CFM fault. All right, and it's got an ID to it. Now, of course, this is much more valuable in, okay, how far is my site from what is the closest site, right? And so I can decide, okay, maybe I'm going to do a new measurement, and I'm going to go from here to the center here, because is that my closest site? Maybe I'll put a measurement here, and then here, and then I'm going to finish, and it's going to tell me, oh, it tells me the area. Okay, so let's delete that. Let's do a measurement again. So I'm going to do from here to here and finish that. So that's 2.3 kilometers. And then I'm going to do a measurement from here to here. And that's 2.56 kilometers. So this is actually the one that I'm interested in. This is my closest location. Okay. So now what I can do is, well, that's the one I'm interested in. I'm going to zoom in and I'm going to click on this. As you can see, I'm going to delete these distance metrics. So you can click on it and say delete. I'm going to delete these objects. Okay. don't think you can delete a marker, but if we hit this line, okay. So now I'm going to interested in this site, and it even, just by hovering over it, I know where I am. I'm at site 11,209. These are the lat long, and it tells me what the PSA with no directivity, because that's what I'm looking at. That's the value. If I click on it, it gives me a heck of a lot more information, okay? It gives me the uniform hazard spectra for all the different return periods and different periods for this VS30 of 760. So if I click on this image, it opens it up in a new place. So, you know, it's a little zoomed in there, but if you click on it, it's going to open it up for you in a new page. If I go here and I look at the hazard curves, and so you can see that there's with and without directivity, and these are the different return periods, and this is for a period of, oh, it shows it for all the periods. That makes sense. And the dashed line is with directivity. So you'll see for, not for all the periods, but for the longer periods, you see it. And honestly, there's not much difference at this site because we're not that near to a fault. All right, so this is useful data. There's also deaggregation data. And this is for a period of 3 seconds, 760 for the site, no directivity. And then these are for all the different return periods. It gives you the M bar, D bar, and epsilon bar, spectral acceleration, and all that information. Okay. And so this is handy. If I zoom into a different site, oh, I got to go back to the other page. Then it also shows some additional data that I haven't quite loaded up here. So I'll show you for a different site where it's been loaded up. Then I've got a series of tables here, and it's a little bit difficult to zoom in because I try to make it so it fits into your image. But you've got the uniform hazard with no directivity, with directivity, the ratio, and the ratio with no lower bound. So if you click on these, it's actually going to open up a table for all these return periods. So if you want, you can just kind of copy the whole table, copy it, and then you could paste it if you want to Notepad, to Excel, to whatever you want. And now you've got all those values. I think if I post it into Excel, it's going to look better. Okay, so you can actually extract the data that's in these plots onto and paste it. You don't have to go anywhere. You don't have to go far. This is the site I'm interested in. Let's get the information. So I've got it with and without directivity, and I try to cram as much information as possible into this data here, but I think it works out pretty well. It gives you some basic information as well. So you could do this for all your sites. Okay, so if I zoom in to a lower site down here, okay, and we'll talk about the data itself, but if you go down here and open it up, now you see two other curves, all right? So for this curves, this is a hazard curve grouped by fault type. So these are the crustals, and this is the gridded. This is down in Southern California, so it doesn't have subduction, but if there was subduction, it would have been in this figure as well. And then the other quote-unquote deaggregation is actually by parent fault. And so we can see here, I've only colored in and highlighted the 15, I don't know how many these are, I think 15 faults that have the highest contribution at a return period of 2475. So I go to the return period 2475, which I believe is this line right here, and I just drew a vertical line down and grabbed the first 15 lines that are at the top, because this is kind of a critical region, because otherwise this would have been impossible to see all these. And so you could see there's a lot of San Andreas and San Jacinto and Imperial Fault. So this is a good way of understanding, hey, this is, so the San Andreas, the Mojave North and the South are the ones, it doesn't mean that they contribute the most. That's not quite the order they're in. And maybe I should have put them in that order. Maybe it is. I don't know. Okay, so then you go back to your map and you say, okay, this was the site, and maybe it's good to put a marker there if you want. Okay, so let's put a marker. Oh, it's difficult to know. Anyways, so this is where we're at. We zoom in and we say, hey, where's the San Andreas Fault? Well, that's pretty far over there. Okay, there are no distances because things get complicated, and so then this is where you do your measurements. You know, this is where I was at. This was the San Andreas Fault. What's my general distance? I'm about, finish it. So I'm about 120 kilometers, and it's interesting, especially because I'm at 3 seconds, and that's why it contributes so much to my hazard, even though it's not the nearest fault. So don't just look at the nearest faults. You also have to look at everything else, because this is not deterministic, this is a probabilistic analysis. Okay, now we've done just, the node directivity. So now let's get something interesting. We go to the next one and we go at the PSA with directivity. PSA with directivity looks like this. So you can go back and forth between them, and it's kind of difficult to, but I did maintain the same color scheme, color map, so you can almost go back and forth. Or you could say, okay, this is the node directivity, I'm happy with what I got, let's open it up in a new page. So it's almost a way of saving that map. And then I'm going to say, okay, let's look at the one with directivity. I keep everything I want, let's open up a new map. And so this is the way I've set it up, that if you want to compare between two different maps, you just have to open them separately. You can maybe split your screen, put this one on the left, put this one on the right, and you can compare them. And I'm hoping the one on the left is the one with directivity, because there's a lot more red. As you can see, it is the same color map. Okay. Then what I did was I actually said, well, wait a minute. So this is handy to have them separately. And then I gave you another combination where you can view them at the same time. And that's what this map is. So this takes a little bit longer to load up. Okay. And what this does is it plots both with directivity and no directivity. The no directivity is actually a hollow circle. But if you zoomed out, you can pretty much see it, right? So let's turn on directivity. It's going to put it on top. And so you can kind of watch the change very quickly by just turning one. Whatever layer you turn on last gets placed on top. So if you want to watch the faults, you just click right here. Ooh, there's the faults right now. Okay, so it's a game of moving layers to the top. So let's put these back to the top and the no directivity one on top of that. So now you can see it going down. So if I turn off the directivity and I zoom in, you actually see that these are hollow circles, but I made the lines thick enough that you can actually visualize them. If you're only interested in the no directivity, you got to go to the no directivity map itself. Now I'm going to turn on directivity, and you'll see that for regions like this, the values are the same because you're not really in that much of a near field. So no directivity is, well, this is with directivity, so it's 0.136. If you hover over the outer circle, it's 0.125. So not much difference between no directivity and directivity. If I go closer, now you see the colors are changing a bit. So if I'm right on the San Andreas fault, you'll see that with directivity, it's 0.423. Without directivity, it's 37. Okay, so there's the difference, and I figure this is a good way of plotting the two. You can turn one off, visualize it. It's not as easy as if it was a full circle, but I wanted to make sure that the two things are visible and understandable, easy to separate them. Okay, so which is not why I made just a bigger circle underneath it. It's just easier this way. All right, so that's a visualization of the data. Again, you click on it, you get all that information. Okay, I made that available for pretty much all of them. So now let's get into something different. All right, changing the period is just different numbers and things like that. So I'm not going to go down that path. But now if I go to the one, so the way that the PSA with directivity was computed was I took the PSA at VS760, the spectral acceleration without directivity and the accelerations with directivity. I computed the amplification factor and then reapplied it to any VS30. Okay, and so I could be doing this and I have a VS30 of 760 ratio, but maybe my SAT class is 300. Okay, this is going to take a little bit because it's loading them all up. So even though this is in it, it's just I redid the calculations, quote unquote, for you, is I take the directivity, I take the PSA with no directivity. I take the factors for VS30 of 760 and I apply it to the no directivity to get PSA with directivity at 300 meters per second. Okay, and so you see here the effect, and it's kind of cool. Look right by the airport. Actually, the airport is over here. There's quite a bit of difference. Okay, if I now select this case or even this case here. Okay, so this is with directivity. Well, it's always more fun to see both of them, okay? So now you zoom out and it looks great. I don't see anything. But if I turn off the no directivity, you'll see is that I only have one region because only in this region where the computations performed at VS30 equals to 300. And that's what was used here. I didn't overlay the maps because there would be some strange discontinuities. So you choose in this region, if you have a site exactly here, I would go and look at this map itself. And interesting, look at that data there. Okay, so this is, because you're right on this fault pretty much. So that's, you don't want to buy a house there. So this is the case here where it's limited data. We turn on the no directivities for everywhere. Okay, but only in this region do we do it for that VS30. So now if we go to, and again, there's fascinating data and you can compare it to, you know, you save this map and then you look at the one for the 760 ratio and then compare and evaluate what it is that you see. Now, if I zoom out, these were done because this is a region where, because the directivity amplification factors are only, or the directivity model was only applied to the faults, not to the crustal faults, not the gridded seismicity nor the subduction event. Now your ratio could be skewed if you have a large contribution coming in from your subduction faults. Again, I would recommend reading the report, but this is my interpretation of that. Okay. And then I think we're set on these values. Now we look at the directivity amplification ratio. Okay, this is the one that I would recommend looking at because it has a no lower bound, or it has a lower bound of 1.0. This is only for this case of VS30. Let's go back to 760 because I like to have the whole map. You can also change the return period, and that just kind of changes the colors a bit. All right, and this is just the ratio. So if you already performed your own code-based design that's been approved by, you know, the project, and you just want to apply your directivity amplification, this is where you come in, and you would have to do this for every period, so you might as well use the site-specific tool that interpolates it. But this is just a good idea to see which regions are affected the most by the directivity amplification, and this is the weighted average of the directivity amplification. This is going to change for different return periods and changes for VS30, but it's a small region where that's different anyways. Okay, and so here you could see hotspots down here and this hotspot here, which I find fascinating because I think it's where two faults are really close to each other, and so they really put their energy together. So if you then want to look at the one, so I'm going to open this up in a separate page to save. And then I'm going to look at the one which is just the weighted models. All it is, and I'm keeping the same color scheme. I'm just adding another color of pink at less than 1. Now you see these regions, and we've talked about this. And if you watch the workshop, there was a bit of discussion on what's going on in these de-amplification regions. Now I can open this up in a separate tab and kind of compare it to the one where I don't have a lower bound. So you see a nice uniform blue here, while here you see pink, but the colors are exactly the same. Okay, the color scheme is kept. And so here it goes all the way down by 0.927, while here it's capped at 1.0. Everything is the same except for the pinks between these two maps. So it's a good way to kind of get an understanding and wonder what the heck is going on. Here it sounds obvious. These other faults are what gets really interesting in directivity. It's not, directivity is not an issue only on the San Andreas or the big faults is really the point here. Then we look at the different models. So different models have different amplification on different regions in different ways. And so here's the BS13, which is pretty much all green. If we look at 2020, BSS 20, we've got some pinks. That's where the de-amplification comes in from this new model. And then CS13 gives us a different set of data. Then these are the amplification factors. If you want to do the fault normal, fault parallel, you've got to be careful because these should really only be applied when you're working with the BS13, but they're actually computed for the whole thing. So if you're interested in looking at what is the fault normal component, you open it up right here and it gets really hot in the fault normal based on the models. Remember, this is models. And then the fault parallel. And this is for this period, okay? It changes for period and return periods, but you almost see here that there's a de-amplification, okay? But these are, you got to report and read the report and learn a little bit more about how these two components work. Then what I have left is just the data. So this is almost, I should have presented this at the beginning. You can see the site-specific VS30. So these were the values that were used for the site-specific. So you can go into the different sites and see. It's kind of cool how it overlays well with the mountains. Then we've got the Z1.0 values. They're only in certain regions. That's where they were provided, wherever we have these basins. Same thing with the 2.5. And then the user faults is just pure user faults, and we've looked at these. The other thing I wanted to show you is, what if I go to PSA with and no directivity, but now I look at the VS30 site-specific. It's gone from my list here, okay? Because the directivity was not computed for VS30s other than 760. So if I go to... Oh, interesting. So that should have appeared. Okay, so this makes sense. I don't have the overlay of the two. But if you're interested in the PSA with directivity, I would start looking at this VSS, and almost this one here is only in certain regions. And so for these regions, it gets interesting. And I guess this is actually everything everywhere. So where it's available, you use the Z.125, Z.1 and Z.25. that are site-specific. Otherwise, it just uses default values. So I find this to be an interesting map because it actually goes into the actual VS30. So to me, it's a little bit more realistic overall. And so now the hotspots are different. Hotspots are still down here, but remember, this is for a certain period, okay? And it's important, the long periods. Now this hotspot here has popped up. Remember, earlier the hotspot was farther south. And so it's really important to also look at what your VS30 is for your site. And I think that's it. That covers the whole maps. Remember, look at the instructions, and I try to explain everything as much as possible. And you can always return to the main page. I hope this was helpful, and let me know if there's anything else that isn't clear. Thank you.